Good day, welcome to the final part of Unit 1. We're talking about chemistry safety. And to be clear, we're not talking about how to do things safely. We're talking about the structure around chemical safety. So kind of the higher level stuff. We'll talk more about how to work safely in the lab and how to handle chemicals later on. Mostly I'll divert you to Hank Green and Crash Course Chemistry for that. Okay, so when it comes to chemical safety, there are 3 government agencies in the United States. This is going to be a US-centric talk because everywhere is different and I'm in the United States. So if you are not in the United States, I'm going to assume things are not that horribly different, at least for Europe, but obviously it's going to be different. So in the US, we have 3 government agencies at the federal level. States may have their own different assorted things. But we have 3 government agencies that are dealing with chemical safety. There's going to be OSHA. OSHA is the Occupational Safety and Health Administration. Their concerns are making sure that business practices and industry is done in a way that protects the worker, the people who are employees of the company, as well as the owners, making sure everyone's safe. But they're focused on if a company is doing something or an organization is doing something, that what they're doing is safe. And they are not limited to chemistry. They do everything from fall danger to skin protection from the sun, everything. But of course, a lot of chemicals have some issues. So those guys are over chemistry. As well as everything else. The next one's EPA, the Environmental Protection Agency. EPA is focusing more so on not necessarily the people who are working at the company, but the people around the company or the organization, the school, the whatever. How are you handling the environment? What are you doing? Now, a quick point, it's easy to think the environment, oh, that's trees and birds and fish, but no, that's also the people. So when you had, the Flint lead debacle, the EPA was supposed to be coming in, stepping in, and protecting the people. Obviously, famously, the director said to the effect, it's not worth our effort for these people. She got fired for good reason. But those are kind of the realms of what EPA is looking for. There have been several environmental disasters. Ohio had a river that caught fire. I don't mean the boats on the river caught fire. I mean the actual river, like the liquid flowing through, caught fire. It wasn't water. And so when your river is that polluted and it catches fire, obviously there's problems. So we're working to clean things up. Lastly, Chemical Safety Board. They're modeled after the Transportation Safety Board. And essentially just kind of like, the same folks who would go do airplane crashes, these guys are built along that lines. When there's a chemical accident of notable magnitude, the goal of the Chemical Safety Board is to figure out what happened and how we can make sure that doesn't happen. They have some wonderful videos online. Disturbing, but great animations of various things, like a granary full of flour exploding. You wouldn't think that, flour, the stuff used to bake bread, would explode, but if you poof it up enough, it'll go. As well as, academic labs getting blown up, etc. So hopefully you don't have anything to do with this Chemistry Safety Board because you're having a bad day if they're coming in. But for all of us, OSHA and EPA are at least supposed to be protecting us and usually do a good job of that. Now, one of the requirements that OSHA sets up is that whenever an organization is working with chemicals, they need to have the safety data sheet. It used to be called the Material Safety Data Sheet, or MSDS, where now we've reformatted them to look more like the international European style. It's a slightly better format, so, the change was good, and it's now called the SDS. Basically, this is a summary of a couple of page summary of the hazards and dangers of the chemical you're working with. This way, if you know what chemicals you've got, you go look at the SDSs and you know how much protection you need. Is this something that's pretty benign where I don't really need much of any protection, or is this something that, yikes, it's dangerous? I better be, as much protection, gloves, face mask, scuba gear, everything, this stuff is dangerous. They are available online, and all commercially sold chemicals are required to have these. The manufacturer will have them and must provide them so that as an employee or as an individual who is using the chemical, you know how dangerous what you're working with is. There's been some interesting discussions on some of the farm chemicals of doing bilingual because a lot of farm workers don't speak English. or have limited English abilities. So we are growing this and expanding it. One of the key parts of the SDSs is they are also pictorials. They do have a pictorial warning symbol. So if you have non-English speaker or non-English readers, I guess it would be, even if you don't have a language that they can read, they at least will be able to see the images, which give you a pretty good clear of or for your chemical. Now, the Hazmat diamond, and this is usually kind of your front line. This is the one everyone looks at first. This is what you see on semi-trucks. When you've got semi-trucks carrying weird chemicals, this is almost always on them. It's actually National Fire Protection Agency 704 for the symbol, but it's known as the Hazmat diamond most commonly, or fire diamond. It's got 4 blocks to it, and it's a way of just quickly labeling it. How bad is this thing? Blue is health. Is it poisonous? These are all rated 0 to 4, 0 being, who cares, 4 being, that thing is dangerous, be careful. So blue is health hazard. Is it poisonous? Will exposure to it kill you? OSHA has their own standard system. It unfortunately uses 1 to 4 or 0 to 4, but it's in reverse. That's more specific. But this one, once again, very nice, very health. Is it going to hurt me in some way? Red, flammability. Will it burn? 0? Nah, not really. 4? Oh yeah, gasoline is a 4 for reference. So it burns good. That's why we use it. But be careful, it burns. Yellow, reactivity, aka will it blow up? 0? No. 4? Yeah, pretty easily. And then white is other. Is it radioactive? Is it a compressed tank? Is it a cryogen? And it's going to have a specialized symbol indicating what is in there. So white is the other. By the way, they're always in the same configuration. So if you're colorblind, you know that right is health, up is fire, left is health, up is fire, right is will it blow up, and bottom is other. 0, no big deal. 4, yikes, be careful. Here's more of an annotated one for an image. A couple points on poisons. The dose makes the poison. Basically, anything will kill you in a high enough dose. The question is, how high enough is the dose that will kill you? Quite often we will talk about that as LD50. By the way, you don't want to get anywhere near the LD50 with exposure. LD50 means how much will kill, how big of a dose does it take to kill half the individuals? Usually done on rats, because, you don't want to be doing experiments like this on people. Now, that doesn't mean that a little bit more, a little bit less is going to be, nice and linear. It could be that even a small dose could kill several people, and you don't want to get anywhere near this for obvious reasons. Bigger the number, the less toxic the chemical is. That means you need a lot more of it to kill you. Now, that said, though, if you're exposed to a chemical over a longer period of time, the odds of a negative health event, which, by the way, LD50 is just dead. It doesn't mean sick. It doesn't mean it's full-on dead. So of some negative health event, whether it's being dead or if it's something else, prolonged exposure, it doesn't take nearly as much. So a small amount over a long time could do as much damage as a large amount briefly, or more. Developing individuals, aka children, are generally more sensitive to poisons as well. So even pound for pound, because almost everything is, you have to adjust for the size of the individual. Even adjusting for the size of the person, children are much more sensitive to poisons. Once again, back to the full flint thing. That was bad for a couple reasons. One, there was a lot of lead. Obviously, it was nowhere near an LD50, but it was still a lot of lead. The water in some houses was legally qualified as hazardous waste. People were exposed for it for a long period of time. They were being told their water was safe and they were drinking it. It wasn't. And those people were often children. And those children will suffer health consequences for the rest of their lives. Now, with chemicals, you've got a couple other things. Bioavailability, which is how readily the chemical can get in you and do something. Obviously, it changes on how it's administered, if it gets on you or in you, etc. Now, thankfully for lead's bioavailability is relatively low. But once it's already in the water, so if you're holding a block of lead, it doesn't really get you in you. But once you're holding water, or you're drinking the water, the bioavailability does go up. That has lead in it. And half-life, or biological half-life. How long does the chemical stay in you? It describes how fast does it, or how long does it take your body to get rid of half of that chemical. Some chemicals, very, very quick, just gets in you, out you. Other chemicals stays in there for a long time. Obviously, the higher the half-life, the longer it stays in you, the more damage you can do. Lead has a half-life on the order of a decade or more. Once again, one of the reasons those children are going to have long effects is because the lead is already in them. It's going to be harming them for the next decade, and then, of course, the damage has been done while the individual is growing, and that could mean developmental issues. Not could mean, it will mean, for many of those children, developmental issues, and lead tends to affect neurons. So it means a lot of cognitive developmental issues. So with poisons, the key things to keep in mind: less is better. So you know, less of it, shorter exposures. Hopefully, the poison has a short half-life, in and out. It's not just going to stay around for forever. And if it can be formed into a form that has a low bioavailability, that helps a lot. That's one of the reasons why when you have mercury spills, you treat it with sulfur. Mercury's bioavailability is not too bad. If the bacteria get to it, it becomes much more bioavailable, much more toxic. But if you can react it with sulfur, then you get mercury sulfide, which is a lot less bioavailable. So you really cut back its bioactivity. All heavy metals tend to have ridiculously long half-lives. Your body doesn't have a good way to clear them. Well, that wraps up the commentary on safety. Obviously, we didn't go into really any details other than, try and avoid poisons and a few things to watch out for. Take-home message: if you're seeing that hazmat diamond and some 4s, be careful and limit your exposure to everything you don't know what it is. With that said, we'll talk a little bit more about safety, etc. in following videos. But this concludes Unit 1. Next up, Unit 2.